Well, hi again, this is Bob, and we're getting ready to take a look at section 8.3, which is basically built on two things. We're still doing hypotheses testing like we did in 8.2, and we also are going back and reviewing a little bit of, I believe it was 7.2, when we were first introduced to the t-distribution. So nothing has changed. In fact, you now probably have much more experience that we understand. We used the t-distribution to set up a confidence interval. You may recall we used the we have a smaller sample size, and we used the sample standard deviation because we don't have the population standard deviation. Anyway, they summarize, and I won't read all of these because we've seen it before, but they summarize everything on the t-test for the mean by going back and reminding us about the t-distribution, about how it, we know it's based on a family of curves that are generated by degrees of freedom. We know it's bell-shaped, especially as we get to a sample size of n greater than 30, the t-distribution starts looking like the z-distribution. It's symmetrical about the mean. Like the standard distribution, mean, median, and mode are equal to 0, and 0 is located at the center. It's like the symmetry line. Like the standard distribution, the curve approaches but never touches the x-axis. Recall that the area under the curve is 1, and which I already mentioned, there were some other things there. As the sample size increases, the t-distribution approaches the normal distribution. Anyway, let's just look at how close. Here's what we've been working with in this chapter. That is based on our central limit theorem and some things we found out in chapter 7. Now, here's our formula for 8.3 because we've got a new set of circumstances where we're going to have to use the sample standard deviation, and we're going to have to we have a smaller sample size. Anyway, the t-distribution still has a sample mean, but in this case, and we still from the sample mean subtract the known mean. This is still hypotheses testing, but notice we've got an S in the formula in the denominator, which is the sample standard deviation, and we're still dividing by root n. The only thing, well, there's two new things in this section, but one of them is just back from a review. We access the t-tables by degrees of freedom, and the degrees of freedom for a t-test, like the chi-squared test, is the sample size minus 1. Okay, so the first thing that obviously we've got, instead of what we learned in chapter 6 and 7, for example, let's just say chapter 7, we learned in chapter 7 that when we were dealing with a confidence interval, that we had values for the tails. This can be thought of as both our z and t distribution, and we had a plus value on one side and a negative value on the other side, whether it was a z or a t. And just to refresh us, what we're doing now is the basic same idea, is we have a non-critical region, and for the two-tailed test, we have critical regions in both tails. Well, it turns out, as you've seen, that what's different from chapter 7 to chapter 8 is in chapter 8, they've introduced the idea of a one-tailed test, and the one-tailed test can be a right tail at a certain confidence interval. Let's say it's alpha equals 0.10. So in that case, we would have 10% of the area in the right tail, and the other 90% would be our non-critical area. And of course, the z or the t-value that separates the critical from the non-critical is called our critical value. And then they also introduced us in this chapter to a left-tailed test. Let's say that we had a left-tailed test at alpha equals 0.05. And so we know that this would be our critical area and that there would be a negative z or t-value there, and everything to the right of that would be non-critical. This is just some things that we should recall. Okay, so the first example, and I'm going to ask you to do the other examples, but the first example is we have to recall, and I've given you homework questions that will help on this, how we find the critical values in the t-tables, and there's only one new thing. Instead of two tails, as I've tried to point out, we can have a one-tailed test. And that one-tailed test can be either in the right tail, in which case the t-value will be positive, or it can be in the left tail, in which case the t-value will be negative. So we're going to do pretty much everything in 8.3, part 1, that we did in the first part of 8.2. So I'm going to look at their example 8.8. So said a different way, a lot of this new material here is just making sure we can use the tables. Okay, so that's why you'll find these from 8.8 down to 8.11 basic table questions with the answer provided. And then you'll also find on exercise 8.3 over on page 449 lots of questions involving the tables. Unfortunately, or fortunately, depending upon how you look at it, if you know how to use the tables, you should do really well on these types of problems. But you've got to be able to pick out the necessary values. Okay, anyway, example 8.8 on the bottom of page 442 says it's find the critical t-value. We've got an alpha equals 0.05. You don't really need to draw this, but it's helpful. And then we've got, now they've already given us the degrees of freedom, so they're telling us the degrees of freedom is 16, and they're also telling us right tail. Just lost my pen there. Now, because they're telling us it's the right tail, we're going, one other thing that I should have mentioned in the, with regard to our t-tables, although I'm sure you've discovered it, and I'm just trying to quickly go back and find the page in the back of the book here. We know we have positive t-values and negative t-values, but when you look at the distribution on page 781, they assume that we know that, and all the values in the table are positive. Okay, so we know, and this is why I say it's helpful to sketch a situation. We know that this is our situation here. We know we've got 5% here and 95% here, and we know that we need a critical t-value here at alpha equals 0.05 and degrees of freedom 16 for a right-tailed test. And a right tail, of course, is just one tail. So if you notice, and this may take some practice, and I'd like you to do 8.9 through 8.11 on your own, but if you notice on the top, and I'll have to go to the fresh screen here, on the top of our t-distribution, we've got our degrees of freedom, of course, but if you notice, they divide that into one tail alpha, and then two tail for alpha. Okay, so obviously a right tail test just is involving one tail at alpha 0.05, so we just go find out where alpha 0.05 goes down to meet the degrees of freedom 16, and we come across. Okay, and the answer is 1.746. Now, just to do the best possible job I can on this, I already mentioned this, what happened if this was a left-tailed test, where we had an alpha of 0.05, and of course this would be non-critical? Well, we would still, for alpha equal for alpha equal 0.05, and if for a left-tailed test, the only difference is we would still follow the same procedure, but we would take the 1.746 and write it as a negative 1.746, because it's understood we're on the left side of the t distribution now. Recall, everything happens in the tails. Okay, well, they give us some assumptions at the bottom of page 443 for the t-test for a mean, and recall, this is when we don't know the population standard deviation. We need it to be a random sample, and n is either greater than or equal to 30, or the population is normally distributed when n is less than 30. So watch for those words there in terms of sample size and the type of distribution. And at the very bottom of page 443, they say, in this text, the assumptions will be stated in the exercise, but when we're doing this in other situations, you've got to check and see that these assumptions have been made. In other words, you probably notice in our class that we don't go out and design our own statistical research. What we do is we take what somebody else has done and we try to interpret it. In another statistics class, you might actually go out and interview or take information from a given population and calculate your own sample mean and your own standard deviation if it's not known, if the population standard deviation is not known, and then draw your own conclusions. At the end of our class, you should know how to do that, even though we haven't officially done it ourselves, but you should have all the tools in order to do that. Anyway, we've got a couple of really good examples that I'm going to do, and then I'm going to stop for this lesson and come back and do the P portion separate. I found by doing shorter, more intense lessons that it sort of spreads the information out into more digestible pieces, if you will. Anyway, let's take a look at, we have the same on 444. You can read up on the top. It's the same basic procedure as we used for the z-test on a mean, except we're going to find the critical value from table F, the t-tables. Okay, and of course our test value will now be arrived at by using this formula. Okay, so now we have something to build on because we introduced and did all this stuff in the previous section. Anyway, we've got a hospital infection, and they tell us that a medical investigation claims that the average number of infections per week in a hospital in southwestern Pennsylvania is 6.3. And since they use the word claim there, that's going to go with our null hypotheses. And then we have a very small sample, a random sample of 10 weeks, had a mean number of 17.7 infections. This sample standard deviation is 1.8. Is there enough evidence to reject the investigation claim at alpha 0.05? Assume that the variable is normally distributed. Recall from the bottom of the previous page, we needed that information. So here's the important part on this question. They didn't, for our alternative hypotheses, nobody is stating or suggesting that the number of infections is more than 16.3 or less than 16.3 for our population mean. In other words, this is going to be a two-tailed test because we really don't know if there's enough statistical evidence to reject that claim or that null hypothesis. So let's get through with the setup first, and then we'll go down and talk about the mechanics of the question here. Okay, and then of course our alternative hypotheses, since we don't know in which direction it's going to follow, would be that it's not equal to 16.3. And recall, okay, so the first thing we have to do is we have to go to our t-tables, and we need alpha 05, but I'm stressing this, it's 2 tails. Okay? And of course, you can go, I just mentioned, and by now, hopefully you've worked through the rest of those example problems, you can go into the t-tables. Alpha 0.05 would put 0.025 in each of those tails, a critical area, and the rest of the graph would be the non-critical area. And we can put the 0 here if we want for our symmetry line. Anyway, recall that the sample size was 10, and so we know that we need degrees of freedom of 1 less than 10 or 9. And the book, and I checked this, gives us a alpha values for left and right tail, there are t values of 2.262 and minus 2.262. Remember, there's symmetry with our distribution here. Even though if we've got a small sample size, we assume that there's symmetry. So whatever value on a two-tailed test that we get on the right side, of course, will be the same value on the left side. Now, you can see how I'm just concentrating on interpreting the answer. I'm going to skip over putting all this stuff in and just report that their t-value was 2.460. Well, clearly, that 2.460 is beyond 2.262. I'll just write it. 2.460 is greater than 2. Where is that darn thing? 2.460 is greater than 2.262. Okay, it's further into the right tail, and that means that there's enough evidence to reject a claim, which in this case is the null hypothesis, that the average number of infections is 16.3. Okay, now in that would be our step 5 when we reject the null hypothesis in this case, because we got a test value bigger than the critical value, or said differently, our test value was further into the tail than the critical value. All right, let's finish off with part 1 here by doing the next question. This is on aspirin consumption. And it turns out that we have a sample size of 12. This is example 813. And fortunately, we do not have to compute the standard deviation in the sample mean. They've done it for us. But let's go ahead and look at what the question has to say. Medical researchers found that people that take aspirin take 8.6 tablets a week. And, they're going to give us this, excuse me. Okay, and a medical doctor wanted to see if he could reduce the number of aspirin. Okay, the moment you hear the word reduce, we should start thinking about left-tailed test. Okay, that's one of those terms that we saw back in the beginning of chapter 8 that sent us to the left side of the distribution. Then wants to see if he could reduce the number of aspirin tablets a person consumes if the subject practiced yoga twice a week. a random sample of 12 people who consumed, who take aspirin were taught yoga, and after the 12-week period, they found that they took the following number of tablets. Okay, well, recall, I might as well write this now. Our alpha is 0.10, and I think we've decided that this is going to be a left-tailed test because it was the idea of reduction. And right now, the established mean is equal to 8.6 aspirin, and we're trying to show that that is not true, or as the medical person claims here, that you will be less than 8.6 based on the yoga treatment or approach. Okay, so the only thing that we don't know, and I've left that to the book and we'll take their word on it, we don't know, but we could find out easy on the sample mean, that it's 6.8 aspirin. Now that's definitely less, but it may not be statistically, and by that I mean using our standard normal distribution, or in this case our t-tables less. And fortunately, we didn't have to go back to chapter 3 and go through the lengthy calculation for sample standard deviation. They told us it's 2.37. Okay, so here's where we're at, and I want to draw the situation, of course, because it's always helpful. We need the cutoff value for alpha equals 0.10 and degrees of freedom n-1, which would be 11. So you'll have to go back into our tables. Now, they're not going to give you a negative value here. You have to know that on this side of the table, the t-value is going to be negative. Remember, we're on the left side of the graph now. This is a left-tailed test. The value you're going to find for t in the tables, though, is going to be a positive value. So you're going to have to remember to find its opposite. And that positive value is minus 1.363. Okay, and then, of course, when they put the t-test on this, they end up with 6.8 minus 8.6. Standard deviation was 2.37. And remember, we use n, not n-1, in the denominator of the denominator, if you will. So we go back to 12. And they tell us that we end up here with minus 2.63. Okay, so let's summarize by using a graph, which can be helpful also, or our distribution here. Now, remember that alpha equals 0.10 isn't that significant, okay? Keep that in mind from the previous section, but our cutoff value was 1.363. When I say negative, of course, when I say cutoff value, I more specifically should say our critical value. And our calculated t-value was minus 2.63. Well, or further into that left tail, certainly, than 1.363. Based on that information, or those numbers, we're going to reject the null hypotheses. And we'll take the assumption that the yoga treatment that the doctor has been giving has been effective according to this study here. Okay, well, I'm going to be back in a few minutes or sometime later today shortly. And I wanted to separate this. I wanted to make sure that we understood, first of all, the similarities between the z-table test and for the mean and the t-table test for the mean. And we went through all the ideas for the t-tables when we were talking about when we were talking about p-values in the previous section, that dealt with our z-tables, and now we're going to finish off on section 8.3 by talking about p-values for the t-tables. And again, I apologize that this gets so wordy sometimes, but hopefully by the time you've done the book questions on the homework and read through this material, it'll make sense, especially as we go on and add new ideas that are based on previous ones. Anyway, I will be back with the second part of 8.3 shortly. Thank you.